Greetings everyone and welcome back to the bench. It's time to do another chip amp done right video, and this time it's with the TEA2025B stereo amplifier ICs. These were submitted by a viewer, just showed up in my PO box. I didn't see a message or anything, so unless I missed it. These showed up in my box, also with a small monetary contribution. So I think the guy's name was Mike. So hey Mike, I really appreciate you doing that. And I will do this video and take a look at these chips. I'm not really familiar with these. Well, I mean, I know they've been around. I just never had one and tried one out before, so this will be the first time. It feels like the first time. So yeah, what I need to do is check the data sheet out, and first I'll put them on a socket board before I solder it up, and make sure everything's working to my satisfaction, and we'll go from there. Let's take a gander at the data sheet. Features: supply voltage 3 to 15, soft clipping, thermal protection, 1 watt, 6 volts, 4 ohms, 2.3 watts, 9 volts, 4 ohms, and so forth. Internal block diagram. Here's the pinouts. Output peak current 1.5 amps, so it's around 1 amp RMS. Electrical characteristics. See the gain here? The gain's really high, 45 dB. It'll be 6 dB higher in a bridge config, so it's 51. Really high gain. But the nice thing is they give you the ability to tweak the gain a little bit, not a whole lot. And we'll take a look at that. Input impedance is 30 kilo ohms, so it's not real high. Maybe not the best thing for guitar use, though you could. The gain's so high, I wonder how it would work. Direct guitar connection. Let's see what else interesting here. Oh, here's the typical applications. We have a bridge mode. It has a jumper. You can connect a capacitor across it and go into bridge mode. Here's single-ended mode, or stereo application. Some distortion. What are we looking at here? Output power versus supply voltage, distortion here. And information on the bridge mode. Whoop-de-doo. Okay, got it set up on the socket board, and not a lot of room. I had to put capacitors under capacitors. It takes a lot of capacitors being stereo, dual channel, so yeah, not a lot of room there to work. You want to keep everything fairly tight and close to the chip, especially your grounding. I had some problems though. I couldn't get this to work. It was sputtering, buzzing, and distorted. And after playing around, I figured out what the problem was. Well, most of these chips, they'll have a couple pins in the center on each side used for ground and heat sinking. Most of those chips tie to a copper slug inside the IC. So, if you measure them with an ohm meter, they're all 0. However, this one is not that way. See if I can get the meter in the shot here. So I have a chip setting off to the side, so if I measure those center pins, I get like, of course the wire is going to be in the way, I get 14 mega ohms. And even the two pins on the side are don't quite zero out. They're low, but they're not as low as if I short the pins out. So if I short the pins, and it's like 0.06, we'll say. If I go across the two heatsink pins, I got to make sure I'm getting a good connection here. So I get 0.2 or see, it's not quite as low. So I'm not sure how they're doing it. Those are not connected or part of a slug, heat dissipating copper slug inside there. It seems like the two pins on each side just go to different ground points on the die, and they're separated across the channels there. So what I had to do, I jumpered across the chip first on the socket board here, and the connection resistance of the socket board wasn't good enough for the chip. So I ended up having to solder the two pins together on each side and then put the copper jumper there and solder that as well. And it works fine. So yeah, kind of a strange setup here with the two pins on each side used for ground and heat sinking. Okay, I got it all hooked up, powering it with 9 volts. It's drawing 40 amps sitting idle here. Connected it to both channels, or both speakers here for stereo sound. Lovely stereo sound. Using my preamp, mainly just for the volume control there and the music source. We'll give you a little demonstration here. Very hissy. That's because of that high gain. Sounds fine to me. It's just a lot of gain, a lot of hiss, so have to do something to tame the gain with this thing. You know, having about 45 dB, that's quite a bit. Okay, I shorted the inputs to ground. I just want to hear how much hiss is coming from the amplifier circuit itself. I don't know if that comes over. Not as bad as I expected. Thought there'd be more hiss. But it is fairly quiet even at such high gain. However, because it has so much gain, it's going to amplify the noise from any device that you plug into it. You know, like this preamp. It'll have a certain amount of hiss or noise just sitting idle. And it does amplify that quite a bit. And you have to turn the level down so low, almost down to the bottom here, to limit the actual music signal going through. So yeah, that's one problem. Like I always say, you only should have as much gain as necessary to do the job, because when you have more gain, then you can have problems with noise. Okay, so here's with the preamp connected, levels turned all the way down. So what this thing is doing is essentially amplifying the noise. You can hear that hiss. Now this has a pretty good hi-fi type chip like an any 5532. Well, that's what it is, any 5532. And even the quietest chip, because this thing has some gain, it's going to have some background hiss that's going to get amplified by this. So yeah, the gain is just too high. So let me see if I can correct that. Okay, so there's a couple things we can do to adjust the gain of the amplifier. We could put a resistor divider network on the input, or just a trim pot, and adjust it to the level we need. That way it will be taking in less signal and any noise from any input device. So that's one way to do it. Another way, or more proper way, is to set the gain lower in the amplifier if it's possible. I know some of these chips have the gain permanently or preset internally where you can't adjust it, but with this chip they do bring the negative feedback pin out so that you can adjust the gain. However, there are resistors internal to the chip already set, so there's really kind of a limitation on what you can do. So according to the data sheet, the internal resistors are 10K and a 50 ohm resistor for the voltage divider of the negative feedback, and then it comes out to a pin where you have to connect a 100 ohm resistor. So if you do the calculation here, pop my calculator here in the way. If we pop in 10,000 divided by 50, we get 200 times. To convert that to decibels, we hit the log button, multiply that by 20. It's hard to press buttons looking through the viewfinder because it's a voltage gain. So that's where we get the gain at. It says 45 on the data sheet. We're getting 46 here. There's a little bit of difference there. It's a little more complicated to calculate the true gain, but this is just back of the napkin calculations here. Okay, so to reduce the gain of this amplifier, we can add a resistor right at this point in between the cap and this resistor, which is internal, because the pin is right at this point. So having more resistance here will allow more signal voltage to come back to the negative pin, which means more feedback, and that'll reduce the gain. I know you're saying, John Audio Tech, just get to testing the amplifier. Well, you just have to go through this stuff to figure these things out, because they do give you a limit. It says on the data sheet that it is not recommended to set the gain lower than 36 dB. And, well, they give the values in dB, so we have to do calculations with the calculator. So back in with the calculator. So let's clear all that out. So they said 36 dB, and we have to divide that by 20. It gives us 1.8, and we have to hit this button here, the anti-log button, which is the 10 to the X. What did I do here? Is my calculator failing? There it goes. Pressing the button, it's not doing anything. We get 63, and I'm not worried about the decimal places. This is not rocket science. So we can take the 10K resistor value in the negative feedback circuit and divide it by 63, 158 ohms. But alas, we have that 50 ohm resistor right there. We have to subtract that off because it's already in the circuit. So we get 108 point blah 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 ohms. We'll just say 100 ohms. So if I pop in a 100 ohm resistor, that'll set this amplifier to its minimum recommended gain, and that should get rid of some of the noise. 36, it still might be a bit high, but that's as low as we can go with this circuit according to the data sheet. Let's give it a whirl. Okay, I popped in the 100 ohm resistor, and I I have the amplifier, or I'm sorry, the preamp turned on. The gain is much better controlled. Now, I have this wire, I can bypass that resistor. So listen to how much louder it gets. Okay, that's bypassed. That's with the resistor. Bypassed again. So yeah, you can see by reducing that gain, we got rid of a lot of that background noise. Now, again, in the real world, I don't need a preamp with this amplifier. It's just that I can, use its volume control during my tests. But I just wanted to show you how you can reduce the gain. And using a 100 ohm resistor is ideal for lowering the gain of this amplifier. You don't want to go any lower than that, according to the datasheet. Okay, I got the 100 ohm resistor on the other channel. Yeah, much less hiss now, a lot better. I'd recommend reducing the gain. The reason you can't go below 36 dB is because probably a phase margin issue. You might have problems with oscillating if you try to send too much feedback around, so they don't want you to go below that 36 dB level. Okay, so what I think I'm going to do, I'll get some power measurements, and I'll actually solder the board up using bridge mode, because this takes a lot of my parts. To make a video, it needs a lot of capacitors, and in bridge mode I won't need as many parts, especially these larger capacitors. Running low on stock anyway. That way we can measure the output power and check everything in bridge mode as well. Okay, I'll do a quick power test. I have 4 ohm loads. This is actually 3.9, but yeah, close enough. Measuring across this 4 ohm resistor here with a scope. Okay, reconfigured this for bridge mode. Certainly a lot less components. And it's in accordance to its little data sheet thing here. There's stereo and bridge mode. And I have a kitty cat on my lap who's hungry and wants food. At 2 o'clock, that's your feeding time, Snickers, but you gotta wait until then. Okay, I hooked it up to the speaker. Oh, that sounds bad. Terrible. Now that's got a bad case of gas, or yeah, it's just not stable here on the socket board. Or I have something hooked up wrong, right, Snickers? Right? Wah. Wah. Well, it's not oscillating, but it sounds distorted. I didn't really do anything, just wiggle some wires here. I don't know, it just doesn't work that well on a socket board. I'm going to have to solder something up. Okay, I have an 8 ohm load. In bridge mode, you really should not go lower than 8 ohms because there's a lot more current involved. Yeah, it looks really ugly. Really ugly. That's why it sounds so bad. But you can see we are getting a better output swing. 3.1 something. I'm not going to bother calculating power. It's just a crappy waveform. Yeah, so what I'll do is solder this up on a breadboard, and we'll do a test there, see if we can get better performance. So here is the amplifier in bridge mode on a perf board. this plus sign looking thing, I used heavy copper wire to act as a ground plane and also to function as a heat sink. Because I'm in bridge mode, the chip will operate a lot hotter because you're doubling the output swing, which into a given impedance doubles the current. So it can mean a hotter chip because you're getting extra power. So you might want to add a heat sink, stick something on top, which you often see with these things. So yeah, it's I didn't need this board to be this large, but I wanted to use up some of these boards I got from Invistia Mall a long time ago. Well, I ran into some problems with this circuit. Here is the schematic and the layout I used. This is looking from the top side through the board to see the wiring. I often do it that way because it's easier for me to visualize the layout. So as you can see here in the input, I have the RF low pass filter, which I always recommend on the input. Bypass the supply with a 220 microfarad electrolytic and a 0.1 film. Now, I did run into a problem. Let me show you what happened here. I'm getting some oscillation. Here's the application circuit in bridge mode on the datasheet. You can see it's simpler than mine. Like I always say, they always oversimplify these circuits so it looks like it doesn't require a lot of components. They're leaving out some important things. But on the output, you see these two bypass capacitors going from the output to ground. Normally you see these with a series resistor. They're called a Bouguereau cell, or some people just call them a snubber network. Well, when I set the circuit up as shown with the bridge application, I was getting a little bit of oscillation. So what I did is added in 10 ohm resistors in series on both legs here, and it cleared it up. So why was I getting that? Well, if you remember, I am running this at a lower gain, with, in other words, more feedback, so I get a lower gain. So I'm likely running with less phase margin. So that could be why. I tried a few things, adding a ceramic capacitor. Those have very low inductance, so they have low impedance at higher frequencies, but that didn't do anything. But the next thing I tried was to include the resistor. I added a 10 ohm resistor in series with the capacitors on the outputs, and that cleared it right up. So there you go. I'll try and demonstrate that on the scope here by bypassing the resistor and see if the thing will oscillate again. So I set up here, I'm just using this board to pass the signal from the preamp into the amplifier. Soldered on a 8 ohm resistor and of course the power supply. Okay, so on the scope here you can see we have a nice sine wave. I don't have any of that distortion I did before like I did with the socket board. Now let me see if I bypass that 10 ohm resistor, if I can get that thing to oscillate, if I can get a good connection here. See that on the top there? It's hard to hold that on there, but see that fuzz on the top there? It's oscillating, messing up the scope triggering. See, I'm bypassing the 10 ohm resistor, and I take that off, it's nice and stable again. So yeah, they're cutting corners on the data sheet. Maybe when it was in a higher gain mode it wouldn't oscillate, I don't know, but in this case it definitely needs those 10 ohm resistors. It needs the proper Bouguereau cell on the outputs. Okay, so let's take a look at the power output here. And here's clipping. And this is kind of weird. I think this is that soft clipping they're talking about. I don't know why it's not soft clipping on the top. Maybe it's just an artifact of using bridge mode. But see, down here, it's nice and clean. But one thing I don't like about soft clipping, it has to start distorting the wave before it actually clips. So it rounds it off a little bit. That's what soft clipping is all about. But you see, as I turn it down, it's still a bit rounded. So that means it's distorting the waveform before it clips. So yeah, I'm not a big fan of soft clipping circuits. I'd rather it just clip. You know, if you're clipping anyway too much, you just need an amplifier that has more power. But if I kind of tune that out, that soft clipping, you know, we're getting around, I'll just say 4.75 volts. And my camcorder battery is about done here. So let me punch this up. I'm getting 2.8 watts of output power into an 8 ohm load with a supply voltage of 9 volts. And we're drawing 580 milliamps off the supply. Well, thanks to Eddie Yahoo over at Kiss Analog, he showed me how to use the FFT on this Siglent scope. If you watch my channel, I was kind of critical of this. Well, it turns out what I was doing, I was not showing enough waveforms. Like with my old Rygold DS1052, I have to show like 6 to 8 waveforms on the screen. But with this one, you have to set it up to show a whole bunch, to collect a whole bunch. You can see how slow it is at acquiring because it has to collect a lot of data. And yeah, you can set the data points to really fine levels here, and you can actually see frequencies that are very close. You can see there's little harmonics actually there. If I turn that down to 1K, you know, you don't see them as much. It looks more like noise. But, you know, I can't say if that's from the scope or from the amplifier. Let me get that off the screen. But anyhow, this is the 1 kilohertz fundamental, 4.5 kilohertz pilot signal. So these little notches would be harmonics from wherever. But, you know, the amplifier is looking pretty clean. If I turn up the amplitude, you can see it's going to start clipping and looking pretty bad. And if I tune that out, it will clean up. Yeah, so no real issue with distortion on this thing. Distortion at 10 kilohertz, and nothing really to worry about. Maybe some small nodes again. I don't know if it's from the scope or the amplifier. Well, I'll have to test the scope, see how clean it is down at these audio frequencies, but I don't really see anything to be concerned with as far as the amplifier goes. Okay, we're looking at 20 hertz here, and there's a little second order harmonic, but you know, it's pretty small. So yeah, I don't think distortion is really a problem with the amp. It seems to be doing pretty well for a little chip amp. Frequency response test, 10 to 100 hertz. Should be at this graticule and this one. We're at 20 hertz. It's almost there. I used a larger input capacitor, 0.47 instead of the 0.22 that they were using. Because we don't have the output coupling capacitors, we don't have to worry about that. So it's better to go for a lower end response, you know, a better lower end response. And you know, we're getting it in this case, which is perfectly fine for a little chip amp like this. And 100. This is the 20 to 20 kilohertz sweep, and you know, it's probably going to be flat. We'll just watch it here. Yeah, it's pretty flat all the way out. It does kind of shrink a little bit because of my music player, but no problems with frequency response. Okay, here's the results of my power measurements. I measured it at 6, 9, and 12 volts. Though the amplifier does run down to 3 volts. You're only going to get a few milliwatts there, but I measured at more normal useful voltages. So in stereo mode, 6 volt supply, I got 0.723 watts, 723 milliwatts at 4 ohms, and 0.42 at 8. 9 volts, 1.74 watts. Very good. We got over a watt and a half, 9 volts, 4 ohms. That's pretty decent there. At 8 ohms, we exceeded 1 watt. That's something I don't see very often with a chip amp. 12 volts, we just missed 2 watts. Again, that's pretty decent showing. And bridged, again, can only test with 8 ohms. You might be able to run it at 6 volts bridged with a 4 ohm load, but I just measured 8. So 6 volt, we got 1.16 watts. At 9 volts, 2.82. Quiescent current draw was around 40. I'd say between 40 and 50 milliamps. The resolution of my power supply, I can't home in any tighter, but you know, it's good enough measurement. So 40 milliamps, it's pretty usable for battery purposes. It's not as low as something like an LM386, but of course this has 2 channels and it delivers a lot more power. Like I said, the minimum operating voltage is 3 volts. Distortion is not really an issue. I didn't see any problems there. And noise is pretty low with the amplifier. But the one issue I did see is the gain. The factory gain is set very high. So that's where I recommend putting the 100 ohm resistor in series with the capacitor on the negative feedback pin. And that drops the gain to what I would consider a more usable level. I mean, you might have a reason to need higher gain, but for connecting music players and things, you don't really want it to have such high gain. So there you have it. Finally got around to testing a TEA2025B stereo amplifier IC. Over the years of me testing, like I said, I did have quite a few requests for me to test something like that. Now had the opportunity to do that. Overall, I think it's a pretty decent chip. I didn't see really any issues, but like I say, you just want to lower the gain for typical audio purposes. And you might want to attach the heatsink. In stereo mode, it does require a lot of parts, and you know, the data sheet kind of misleads you a little bit on the components. I did have to put the proper Bouguereau cell components in the output of the amplifier, so you know, to keep it from oscillating. But yeah, other than that, it's a pretty good chip. If you want to help support the channel, check me out over on Patreon. Link in the description. And we'll catch you on the next one. Thanks for watching. Okay, to reduce the gain of this amplifier, yeah, thank you too.